Okay, so now that we've covered differentiability, the limit definition of the derivative, and the alternate form of the definition of the derivative, um, we can cover more complex AP-style questions that really um, force your brain to think about these definitions and how to understand the algebra behind it. So we'll start simple first, just kind of reviewing some of those concepts. So you can see here, the first example is to list all the spots where the function is continuous or not continuous and be not differentiable. So if you want to go ahead and pause the video, I'm going to put those answers up in a second. Okay, so we have one discontinuity here. It is at x equals 6, and a corner at x equals 3, a vertical tangent at x equals 4. A discontinuity is still needing to be mentioned, that, again, the function's not continuous at a point, the function will also not be differentiable, so the discontinuity is kind of falling into both categories. And then a cusp at 8. Okay, so next question is, at which labeled points is the slope of the graph 0, positive, and negative? Again, if you want to pause the video, I will pop those answers up in a second. Under quick analysis, it appears that the graph has a horizontal tangent at B, right? So the slope there would be 0. AE, same thing, slope is 0. Positives at C and D, negative at A and F. And again, it's all about the increasing and decreasing nature. Okay, so now we're going to get to a more challenging question. Let f be a function that satisfies f of 2 plus h minus f of 2 as defined as such. For all real numbers h, find f prime of 2. So again, if you want to pause the video, I'm going to work through this one with you guys, though. It's really dependent upon knowing the limit definition as such. So the f prime of 2 is defined as the limit as h goes to 0 of f of 2 plus h minus f2 all over h. And so by substitution, now we could just say that the numerator can be rewritten as the polynomial 5h minus 3h squared plus 9h cubed all over h. Notice again that all of the terms in the numerator have an h in it, and that's usually how these derivative examples usually work out once we simplify. So we could factor an h out, or you could just distribute that division of h to each term, which would then cancel out and drop the degree down by 1 on each of these. So now we're looking at a limit of 5 minus h, or sorry, a limit of 5 minus 3h to the first plus 9h squared. And so by direct substitution, if we plug in 0, which we can now because we're not getting indeterminate form, I can actually cross out this and this, right? If I plug in 0, those go away. And so we end up getting an answer of 5 for this one. Okay. All right. So again, kind of a tricky example, forcing us to understand function notation, how to manipulate this using the limit definition. So this one says use the definition of the derivative to find f prime of x. So if I flip back real quick, we just did f prime of 2. So when it was f prime of 2, I had 2 plus h and 2 in the parentheses. So if I'm trying to find f prime of x, f prime of x is going to be the limit as h goes to 0 of, and again, I'm using the original definition of the alternate form because this one in particular is telling me that the limit at h goes to 0. And that definition is f plus h minus f of x over h. And essentially, we're going to take this expression here that was given to us, and well, f of x plus y is defined as this. F of x plus h is going to be defined very similarly, right? I could just replace all the y's with h's, so I could rewrite this as h goes to 0 of f of x plus h is now going to be f of x minus 4 f of h, right? I'm replacing this with an h, plus 9x h again, replacing my y's with h's. So that's f of x plus h minus f of x all over h. And it looks kind of confusing at first, but we have some things that cancel. We have positive f of x and negative f of x. Those are going to cancel. So now we get the limit as h goes to 0 of negative 4 f of h plus 9xh, or hx, over h. Now I can't cancel the h's out, right, because this is in function notation, so I can't cross that h out there. But I can kind of still think about it as distributing division, right? I could think about this as two separate limits. It's one of our limit properties that we discussed. I could really view this as two separate limits. The limit as h goes to 0 of negative 4 times f h over h plus the limit as h goes to 0 of 9hx over h. Right, I just distributed that division, divided both of these terms by h. So the reason that works out nicely is because right over here in this example, the h's cancel. So for that expression, we just get 9x. The limit as h goes to 0 of 9x is still just 9x. And then for this one, I need to use this piece of information right here. And so the limit as h goes to 0 of f of h over h is 2. So negative 4 times that would be negative 4 times 2. So essentially, my final answer here is negative 8 plus 9x, or 9x minus 8. All right, so last question here gives us the limit or alternate form of the definition of derivative. So this is essentially stating that if that limit is true, again, we would end up with indeterminate form. But if that limit does work out to be true, that is the definition of saying that the derivative exists at 5 and the slope there is 3, which tells us that this must be true. Right? The function is differentiable at x equals 5, and the derivative comes out to be 3. So for that reason, then b can't be true because, I mean, this is just a function notation thing. A function is defined as each input having only one output. Derivatives are a function. So the input of 5 can't have an output of 3 and 0 at the same time. So this is never true or not true. It's impossible. So essentially what we know is that we have a graph where at x equals 5, who knows what it looks like, but we have at least the idea that at 5, it appears that the slope would be positive 3. Now, the y value at 5 could be anything, right? I could have this graph where I have it right now. It looks like maybe this could be 1, 2, 3, right? But I could have shifted it down here, made my graph look like this, and this would have a slope that still looks like positive 3. So this one might be true. F is continuous at x equals 0. I had no idea if that's true, right? We could have There's no information that tells me about what's happening at x equals 0. The information we have is about what's happening at x equals 5. So sure, this could be true, might not. You can see that the graph I have to the left, I didn't actually reach the y-axis. I could have an asymptote there. I could be going through the y-axis, so that might be true. For E, again, this is true if the function has a derivative based on differentiability rules. It has to be continuous at that point, so this is a must. And then because it's continuous, based on what we talked about in continuity at the very beginning of this unit, that the limit at 5 and the function value at 5 have to be the same. That was the basic definition of continuity. So if this we said was a must, then this is also a must. Kind of tricky. Really trying to dive into the understanding of the language on that one.